So now that we've established this sort of basic working definition, let's think a little bit about what controls the climate of our planet and in truth of any planet. And at the biggest level, climate is controlled by the energy balance of a planetary system. So there are really three things that control the climate of Earth. How much energy is coming in from space? How much of that energy is reflected before it is absorbed? So you could imagine, for example, that if there's a big white cloud high in the atmosphere and sunlight is coming in, some of that sunlight will come through the cloud, but a lot of it will be reflected away. So that doesn't really affect the lower atmosphere because the cloud is acting as a mirror. And then for that energy that hits the surface of the planet, in this case of the Earth, that energy is absorbed and then re-radiated back into space, and I'll talk more about that in just a minute. And how much energy then escapes back into space is the other thing that sets the energy balance of the planet. And so at sort of the largest level, the things that matter are incoming radiation, outgoing radiation, and how much is absorbed versus reflected. I'll go over those each in detail in just a minute. Now, I said a minute ago that climate is not just temperature, it's also rainfall and the seasonality of that. Rainfall is the result of water circulation that is itself driven by this incoming solar radiation. So sunlight comes in, it warms the ocean, water evaporates, and then there's differential heating and cooling on different parts of the planet, and that creates winds which move that water around. And so the evaporation of water and the movement of water in the ocean as a result of different heating and cooling on different parts of the planet at any given time are what result in the circulation of moisture and the eventual return of that moisture to the Earth's surface. So rainfall itself is also driven by these parameters. And then seasonality, which I talked about as sort of the third feature of climate, seasonality is also a result of differential heating and cooling of the Earth's surface. So for example, as the Earth's North Pole tilts towards the sun, we get the northern hemisphere summer. And then as that axis points away from the sun in the winter, as the Earth orbits around the sun, then we get the northern winter. And it's differential heating, both of the land surface and the ocean surface, that gives us the seasonality that different places experience. So while the climate of a place is a description of its average temperature, its average precipitation, and the seasonality or changes over the year, what I want to focus on first when we're talking about Earth's climate is temperature. In order to understand what controls the temperature of the Earth, we need to know three fundamental things. We need to know how much energy hits the Earth's surface in a given amount of time, how much energy is absorbed by the Earth's surface versus reflected back into space, and how much energy is radiated from the Earth's surface back into space. So in order to talk that through, I'm going to give you sort of a cartoonish example, and then we'll move to the Earth as the system of interest. But let's start with a cartoon understanding. Imagine a surface, shown here on this slide as a purple surface, so a fairly dark color, and it's receiving a certain amount of energy in the form of sunlight. Let's just, for the sake of argument, say 10 units of energy. Now, it's a purple surface, not a black surface, and so it's not perfectly absorbent. It's reflecting some of that energy without absorbing it. So in this case, in the cartoon example, I'm going to say 1 unit of energy is reflected. So 10 minus 1, or 9 units of energy, is absorbed by that purple surface. Now, the laws of physics tell us that if an object is receiving more energy than it is emitting, it will actually heat up, and it will emit energy in proportion to its temperature. Actually, in proportion to the temperature to the 4th power, but in proportion to its temperature. So in the case of our purple object here, receiving 10 units of energy, reflecting 1 unit of energy, that object will heat up until it's hot enough to radiate back out 9 units of energy. And once it gets hot enough to emit those 9 units of energy, it will be in energy balance, and its temperature will not change anymore. So think about a pot of water on the stove. It's sitting at room temperature. You turn on the heat, right? Now all of a sudden, the pot of water is receiving more energy than it is emitting, and the water will begin to heat up. And if you hold your hand over the water, or even worse, put your hand in the water, you will feel that that water is hotter than it was before, right? So here's our purple surface, receiving 10 units of energy, reflecting 1, heating up until it emits 9 units of energy. There are 3 things that are really important to remember about this example before we go on to the next one. If an object absorbs more energy than it emits, its temperature will rise. If the object emits more energy than it absorbs, its temperature will fall. So for example, with the pot of water example, once that hot water is hot, if you turn off the gas, now all of a sudden that hot water is emitting more energy than it's absorbing, and it will cool back down. And if an object absorbs and emits the same amount of energy, then its temperature will stay constant. Okay? So with those 3 concepts, I want to add one more cartoon example before we move back to the sort of planetary system. So now I want you to imagine this blue surface, a lighter color than the purple. And it's getting the same 10 units of energy coming into the system. In that case, it's reflecting some, and it's reflecting a bit more. It's brighter. So in this cartoon example, we're going to say it reflects 3 units of energy. It's still not an energy balance, though. It's getting 10 units. It's reflecting 3. So on net, it's absorbing 7. And that object will heat up until it's hot enough to emit 7 units of energy. Now, because the temperature of an object is proportional to the amount of energy it emits, what this means is that the purple object will heat up more than the blue object for the same amount of incoming energy. You intuitively know this. If you have a white surface and a dark surface, like a white sidewalk and a black asphalt road next to the sidewalk, on a hot sunny day, the black asphalt road is much hotter because it's absorbing more energy, reflecting less. So that intuition actually plays a really important role in thinking about the Earth. And what I want to stress here is that it is a basic property of matter that the energy it emits is proportional to its temperature. So we're going to move now from this cartoon example and this basic understanding of the physics of energy balance to a more complicated system, the Earth system. In order to do that, we need to just think about this in a slightly mathematical way. So if we know how much energy is hitting an object and how reflective that object is, we can calculate what temperature it has to be in order to radiate enough energy to maintain a constant temperature. That is, we can calculate what the purple object temperature should be and what the blue object temperature should be. So let's think about that for the Earth. Here's a cartoon of the Earth, sun on the left, Earth on the right, sunlight coming in, and we know how much sunlight hits the Earth's upper atmosphere every second. We know how much energy is coming in. On average, about 342 joules of sunlight energy, and joules is just a unit of energy, comes into every square meter of the top of the atmosphere every second. So we say that's 342 watts per meter squared of energy. It's not uniformly distributed. There's more coming in at the equator, less coming in at the poles, nonetheless on average. And we know that the Earth is not perfectly reflective, nor is it perfectly absorbent. And on average, again on average, about 70% of that incoming energy is absorbed and about 30% is reflected. Of course, that depends on whether there are clouds or continents or oceans, but just on average. So now that we know how much energy is coming in and how much is reflected versus absorbed, we can use those basic properties to calculate what the expected temperature should be. I'm not going to make you go through the calculation, but it's a very simple equation. The only variable in it is temperature, really, other than the ones I've mentioned here. If you do that calculation for the Earth system, you get a number that is wildly wrong. So we can calculate the temperature, we know the laws of physics work, but when we do this, we get an answer that the Earth should be negative 18 degrees Celsius, that is 0 degrees Fahrenheit, which would mean the Earth was permanently frozen, which it is not. So there's something wrong with the way that I'm describing this system in terms of energy being incoming and energy reflected. We need to add one more thing to our understanding before we can understand the basics of Earth's climate. So I'm going to go back to the cartoon example. Here's the blue surface again, and Earth is approximately blue. It's mostly ocean. And let's think about this example, but add one more complexity. So you have your incoming radiation, your incoming solar radiation, your incoming sunlight. Let's again go back to this simple cartoon that it's 10 units of energy, okay, just for ease of calculation. And as I said, the Earth is reflecting about 30% of that energy. So going back out, there's 3 units of energy. But I'm going to add one more thing to that. I'm going to add a layer close to the Earth's surface that I'm showing by this dotted red line. And that layer has an unusual property. It has the property that it lets most of the incoming sunlight in without any problem. And so these 2 yellow arrows, they're not really affected by this layer. But this layer has the property that it traps some of the outgoing radiation, which is a different wavelength of radiation than the incoming sunlight. In this example, the blue surface heats up to emit 7 units of energy, but that red dotted line traps a little bit of it and re-radiates it back down toward the Earth's surface. So it allows 5 units to escape in this cartoon example, but not 7. 2 of those units get re-radiated back down to the Earth's surface. So now let's think about the energy balance of this system. There's 10 units of energy coming in as sunlight. Another 2 units of energy on the right-hand side, that slanty arrow, are coming back from the red layer. So that's a total of 12. Whereas what's escaping the surface, the blue surface, is 3 units that are reflected, that's the yellow arrow, and 7 units being emitted. And so what you have here is an energy imbalance. You have 12 units hitting the surface and only 10 units leaving the surface. As a result of that, you have an energy imbalance with more energy hitting the surface than is being emitted. And as a result, the surface has to heat up. So in this case, the surface is receiving 12 units of energy, 10 plus 2, but only losing 10 units of energy, 3 plus 7. And therefore, it has to get hotter. So the addition of this red dotted line, this layer that traps a little bit of energy, the addition of this layer makes the surface heat up. Think of it as putting a blanket on you. You're lying on the couch, you're cold, right? You have some equilibrium with the air around you. You put that blanket on, and now all of a sudden, some of that heat coming off of your body is trapped and re-radiated back towards your body. And as a result, your skin warms up. In the case of Earth, this is not a visible blanket. It's invisible, but it's there nonetheless. And it is the atmosphere, and specifically some small constituents of the atmosphere, small in terms of their amount, but important in terms of their energy balance. And these are, of course, the greenhouse gases. Greenhouse gases are trace gases in the Earth's atmosphere that have the particular property that they are good at absorbing radiation of the kind that the Earth emits. They don't absorb much of visible light, which is the light that's coming in from the sun, but they do absorb in the infrared part of the spectrum. It's a longer wavelength light than our eyes can see. And that is the wavelength of energy that Earth emits. What are those greenhouse gases? Well, there are 4 main constituents that occur in nature. The first and most important is carbon dioxide, CO2. We'll talk a lot about that in this class. Methane, CH4, is another strong greenhouse gas. It's quite a bit stronger on a molecule per molecule basis than carbon dioxide, but there's much less of it in the atmosphere. Similarly, nitrous oxide, or N2O, is a very, very potent greenhouse gas. We'll talk a lot about that when we come back to the section on agriculture. But nitrous oxide, although it's very potent, is also much less abundant in the atmosphere than CO2. And water vapor is a very strong greenhouse gas in itself. But as we'll see in future modules, the amount of water vapor in the atmosphere is a result of its temperature and doesn't drive its temperature. We'll come back to that in a later module. So these greenhouse gases act as an invisible blanket. They trap some of the radiation that would otherwise escape back into space. And as a result of trapping and re-radiating that radiation back towards the Earth's surface, the Earth's surface is not in a perfect energy balance in terms of incoming radiation and reflected radiation. You need to take into account the amount that is trapped by greenhouse gases. And when you do that calculation, that is, when you include not only how much energy is hitting an object, how reflective that object is, but also how much energy the atmosphere traps, then we can do a calculation that actually gets the temperature of the Earth really right, or very close to right. We can calculate this temperature, and when we do, it comes out at about 16 degrees Celsius, or about 61 degrees Fahrenheit, which is the average temperature of the Earth. or I should say, which was the average temperature of the Earth, because of course, if we change greenhouse gas concentrations, as we'll talk about in just a little bit, then you would expect that the amount of energy that gets trapped on its way out increases, and as a result, the system will heat up. So moving now from the cartoon version of the purple surface and the blue surface, what I'm showing you here is still a cartoon, but a slightly more complicated one of the major controls of Earth's temperature in terms of incoming and outgoing radiation. So on the left of this cartoon, you have the incoming sunlight. Not all of that sunlight even makes it through the atmosphere. Some is reflected. And then, of course, some hits the surface and is also reflected. So what you see on the left in the yellow arrows is the amount of sunlight that actually hits the Earth's surface and gets absorbed. In the middle of this diagram, and I want you to maybe pause the video and take a look at it and really think about these different quantities. In the middle of this diagram, you'll see the sort of greenhouse gas story that I was just telling you. So there's a bunch of energy shown in that sort of fat orange arrow emitted by the Earth's surface. Some of that escapes out into space because greenhouse gases don't absorb in that particular wavelength. But some of it is actually absorbed by the atmosphere. And once it's absorbed by the atmosphere, it can be re-radiated in all directions. Some up to space, just sort of continues on its way, and some back down to the Earth's surface. And as a result of that interaction between the atmosphere and outgoing radiation, the Earth's surface warms up. We won't spend a ton of time on the far right part of this diagram, but just for completeness' sake, there are transfers of heat within the atmosphere that are important for understanding atmospheric dynamics. And I'll just mention them briefly, although they're not super important for the story at this point. Some energy is transferred from the surface up into the atmosphere by the rising of hot air. So you've probably heard that hot air rises, and when it does, it's transporting heat away from the surface and up into the atmosphere. And another thing that affects the distribution of heat within the atmosphere is this property of so-called latent heat. So if you evaporate water off the surface and it rises up into the atmosphere and then condenses back into rain or snow, that process releases heat. So evaporation absorbs heat. The phase change from liquid water into vapor absorbs heat. And then when that vapor condenses back to water, it releases heat. And so if you have evaporation off the surface and condensation in the upper atmosphere, or higher in the atmosphere, that also releases heat. Those are the two arrows on the far right. I really mentioned them for completeness sake. We're going to focus mostly on the incoming solar radiation in the yellow and the greenhouse gas effect that you see sort of in the middle of this cartoon. So, to reiterate, what controls Earth's temperature? It's the amount of incoming radiation from the sun. You'll hear that sometimes called insolation, not to be confused with insulation, which is what you put in your house, for example. So the amount of energy coming in from the sun, whether that energy is reflected or absorbed by the surface, which is controlled basically by the color of the surface and the roughness of the surface, and then how much radiation actually escapes back into space. And that is controlled by the concentration of greenhouse gases in the atmosphere.